Yeah, hello. This is another video of our series on machine learning using R. And today I'm going to talk about how to perform support vector machines analysis. So support vector machines is another big class of machine learning algorithms. Here's a brief view. Um, SVM is a supervised algorithm for classification and regression, finding the best hyperplane to separate classes. And it maximizes the margin between classes using support vectors, the closest data points to the decision boundary. And SVMs handle both linear and nonlinear data with kernel functions, making them versatile. And they are memory efficient, relying only on support vectors, and work well in high dimensional spaces. That's actually what makes them powerful. Okay. SVMs are robust to overfitting and outliers, especially with proper parameter tuning. Also, their advantages. So I think it's a generalization of linear discriminant analysis using just one hyperplane to separate data points, but now you have multiple supported machines, so it even works for nonlinear boundaries. All right, the R package for implementing SVMs is the library e1071. Okay, so we're gonna load that library in, and we're gonna load the caret library in, set random seed, create a sample data set. So we have the dependent variable y with class 1 and class 2, and x1, x2 as two predictors. So this is a very simplified example. We can have much more complicated data set for support vector machines. Okay. First, we want to split the sample into training and testing data set. So create a training index by using the create data partition. This is from the caret library. So the data at y and probability equals 0.7 and least equal to false. And then we just split the data into training and test data. And now we can implement SVM using this function SVM from the e1071 package. It has several kernels. They are linear, polynomial, radial, and sigmoid. So let's do a little bit of trick. We put all these four names into kernels, and then we do a loop for k in kernels. We fit SVM model and use SVM y tier the dot and data equal to training data set and kernel equal to k. So we're looping through the kernels, fitting one SVM for each kernel, and then we print it out. We print out the number of the kernels and then the information of the kernel. Okay, so here, let's go back here so you can see the first one's a kernel is a linear, so we do a linear kernel, and you can see the SVM type is C, so for classification, SVM kernel is linear, and cost is 1, number of supported machine, supported vectors is 18, and divided in 9 and 9 in two classes. Okay, and number of classes is 2. Levels are class 1, class 2. Second one is kernel for polynomial, and SVM kernel type is polynomial, and it has cost 1, degree from 3, so it's a cubic polynomial. Coefficient 0, that's a offset term. It's 0. So, and there are 25 supported vectors in this SVM. Okay, and 12 in class 1, 13 in class 2. And for the third one is the radial kernel, and it has 29 supported vector machines, 15 in class 1, 14 in class 2. And the last one is sigmoid, and it is 28 support vector machines, 14 in each class. Okay, so a little bit note here. So for the linear kernel, it creates a straight line, a decision boundary, best for data that is already linearly separable. Okay, and polynomial kernel that forms curved boundaries useful for capturing polynomial relationships, okay, between features. So it's kind of a nonlinear boundary. Okay. And you can use the RBF, the radial kernel, like handles complex nonlinear patterns by measuring distance between points, often the default for unknown data structures. So this is pretty the very flexible option here. Okay. And sigmoid kernel is models S-shaped boundaries, commonly used in neural network applications. Right. And then with more interpretation of these things in the output, the cost parameter is to control the trade-off between minimizing misclassification and maximizing our margin, the gap between classes. So you're doing a trade-off there. And here, higher cost means more on reducing misclassification. Okay. And the coefficient 0 is an offset. The number of support vectors in a support vector machine refers to the count of data points that are closest to the decision boundary, the hyperplane, and directly influences position and orientation. The higher the number, the more complex the boundary is. Okay, but there's still like a dimensionality reduction because you don't use the whole data set. You're just using this the support vectors, the points. Okay. All right. And then we can also use this pack to do some fine tuning of the hyperparameters. The function is tone, so SVM and ytilde data equal to train data. Now we specify ranges equal list cost equal to C 0.1110 and gamma equal to C 0.1110. So again, the cost is the controlling the trade-off between reducing misclassification and maximizing the gap. Okay. The gamma parameter is relevant for the nonlinear kernel like RBF, controls how far the influence of a single training example reaches. So these are the two hyperparameters. We can actually use the training function to train them for the data at hand. So let's run that syntax. And it's finished pretty quickly. So we can print out the best parameter. Here it gave us the cost is 1, the gamma 1. So just saying we kind of not very extreme in the trade-offs. They're pretty balanced out. And also, I think the fine tuning didn't really give us much changes. We also got the cost equal to 1 by just running the SVM machine, right? The function. And prediction with the decision values. We can do prediction using a classifier. So we can use the tone at best model and then test data set now. Decision rules equal to true. So we want the decision rules. And we do that and we can get to the decision value. And here's the decision value, which is, you can see this output for these data points. And you can see the class 1 over class 2. If it's a positive value, means this belongs to class 2. Negative value means it goes to class 1. And the larger the absolute value, the more confidence we have about the classification. So if we got something really close to 0, for example, and this like 0, like 32 here, negative 0.02. So that means we're not very confident about this classification. Maybe this is very close to the boundary. All right, and we can do some plots. We can plot out the toned best model used on the training data set, and we can do it for only two-dimensional data. Okay, so this we get x1 and x2, and you can see this a pretty complicated boundary. It's a nonlinear. It's kind of piecewise. Okay, it's gonna get that out. We do have some, you know, mix up of the data points, so it's not doing a perfect job. All right, and also we can do cross-validation about the accuracy. So we can use the SVM fit white here the dot and data equal to training data. We can specify cross-validation equal to 5, so we only do 5 folds cross-validation. Actually, the default is cross equal to 10, but I tried that. Actually, the accuracy is the same. Both give you 95.77, so it's very high accuracy from the cross-validate accuracy. But then I remember that we did not compute the raw accuracy, so we can use this. So the manually calculate, the prediction in the test data set, and over the number of rows of test data set, and the correct the raw accuracy is 93.1%. Okay, so the cross-validated accuracy is actually higher than the raw accuracy, which is not happen very often, which just happen to this data set we have. Okay, usually the cross-validated accuracy should be lower than the raw accuracy. And also we can print out this classification report is a table. You can see actually it's pretty good. Only there's also like class 1, class 2 that off diagonal. There's the 2 cases misclassified. Okay. All right. I think this is a brief introduction of the implementation of support vector machine in R. And if you like this video, please subscribe to our learning channel and recommend this video to other learners who might be interested. Thank you very much.